Are you all ready? Okay, so hello everyone. My name is Marcin Moskała. I am creator of Kotlin Academy, author of the book Android Development in Kotlin. And today I am here to talk about Kotlin Coroutines. I believe since we are on a general conference, there are two kinds of people in here. There are front-end developers and back-end developers. And both of you have a bit different motivation for Kotlin Coroutines because they face a bit different challenges in their everyday job. And therefore, a bit different aspects of Kotlin Coroutines are important for you. Oh, if you have any questions, just hands up and you can, I will stop during the presentation. So front-end developers and back-end developers. Let's start from front-end developers, and by front-end I mean not only websites, but also Android, iOS, desktop. This is typical front-end problem. We load some data from some API, we make some processing, and we display it on our screen. It doesn't work because we cannot load data from API on main thread. We either freeze our front end or we have an error like in Android. So we cannot do it this way. We can pack it into some thread, but again, it won't work because we cannot display stuff on in most systems, you cannot display stuff on a separate thread. We need to get back into main thread, and this is an implementation of this simple problem that works, but it is not a good implementation. I think it is a very bad implementation actually. All this juggling with threads and switching and coming back, it is hard and it is just problematic. There are a few approaches that are trying to make it better. First one is to use callbacks, and this is actually a valid approach. We just say send this request, and once we have our data back, we will we'll go with the rest. It works, but this is a very simple problem. Let's say that we have 3 requests, get some data, get some configuration, get some API, and in callbacks we would implement it this way. This is a very bad implementation for 2 reasons. One of them, it's not simultaneous, and it's very hard to make these all 3 requests in the same time. And right now it takes 3 times longer because you need to make a request for first endpoint, wait for a request, make for another one, wait, make for another one, and wait. So it's very bad implementation. And second one is this. This is called callback hell. This indentation is very problematic in long term, and it's hard to extract functions from that. Hardcore examples can be found on the internet, most of them from Node.js, where callbacks are hardly used. We don't want that. So callbacks are not an answer for us. Another very popular in Android, since I'm coming from Android world initially. Right now I am full stack, but I used to be an Android developer. Is to use reactive X, in this example RxJava. We make some stream, we say where we subscribe, where we observe, we are mapping, and finally we display this. This is a good implementation, but it's pretty hard when you look at that, and a lot of code, a bit complex. It's not so clear what happens there. Our second problem can be also easily solved using this Rx approach, but you can see another limitations in here. You cannot pass. You need to pack these all requests into one, in this case triple, and unpack it in our function. And again, it's pretty big and complex. My answer, I think that the best approach is to use Kotlin Coroutines, which are, from this point of view, a new approach, but from the theoretical point of view, they was in programming since the beginning. And in Kotlin Coroutines, our problem solution would look like that. We first say, launch UI, that we want to launch it on UI thread actually. Then we obtain our newses, and then we process and show it. But when we get our newses, we don't really wait for our request. We don't wait it on this thread. When you send the request, you suspend this execution, you say, okay, free the thread, stop this function, I will get back to that later. UI thread can be used to other problems, your application is still running, and once you have some response, you are getting this UI thread again, and you continue with the function. Another problem, a bit more difficult, when you have two calls, but second one needs the first one. Also very simple and flat, in opposition to callbacks. It is flat, so it's more readable, easier to extract, etc. You first get config. Once you have it back, you send get news request. Once you have it back, you process it and show it. Our problem with free simultaneous requests, you can just use interface deferred from Coroutines library. Deferred has function join. Join is a suspending function. So we first send all three requests, and then we await for them once we invoke join. So we await for them later. So this is a very simple solution for this a bit more difficult problem. A few other simple examples of coroutines. Let's look at that. You can use coroutines inside the loops. Not a problem at all. You can imagine implementing that using callbacks. So we take like a first page, fill this page, then a second page, fill this page, etc. And you can also easily add error handling for these coroutines. And it's like a normal error handling you do all your life, you know. This is like making this for is as simple in RxJava. It's just a flat map. But what about error handling? One of them is simple. But what about another one? How many RxJava developers do I have in here? Hands up. Okay, not enough to make it reasonable, but it's not so simple to make to think about separate error handling for like everything and for concrete requests. Okay, so this is how coroutines can help us with programming, but in Frontend. But what about Backend? I believe Backend gets even more from coroutines. A typical problem in Backend is following. You get some data from database, you make some processing, and you respond it. This is supposing that this is a very simple framework. This would run on main thread, so you cannot block main thread for this database call. It's not acceptable solution. Better solution would be to start every response, every call in a separate thread. But remember, you just had a presentation about it if you were there. Threads are not cheap. Threads are actually pretty expensive. And now imagine that your API gets 10,000 calls a second. Thread takes around 2 megabytes on RAM. Let's say your database takes around half a second to respond. So as a result, you need 10,000 megabytes of RAM all the time. This is like unacceptable in your backend. Instead, you can use coroutines and you launch it on some pool of threads. You take one thread before this database call, then you suspend it, you release it, and once you have response, you take some other thread and you continue from there. I want to show you a very simple demo that presents that. This is like a simulation of first example. We have 100,000 threads. Everyone waits and then prints a dot, and we await for all of them and say done. What will happen? First we have some dots printed pretty slowly, then we have out of memory error, and then some dots from rest of the threads that were already created. As you can see, it's impossible to make such an amount of threads in the same time. How many threads we can do in my computer? Let's see it. Okay, around 10,000 threads. That is a limit of my computer, and I have pretty good computer. Let's try it now with Kotlin Coroutines. Direct equivalent in Kotlin Coroutines is following. We launch this works. We make delay, and then we print some dots, and we await for all of them. As you can see, 1 second, immediate response, and it's done. You might notice it's far faster than it was with threads, you know. In threads it was printing, and here you have nearly immediate, and it's all printed, you know. So it's much faster, because coroutine creation is much faster than thread creation. Good backend can give us this this starting in suspending context out of the box. So in normal implementation, we will just make something like that: implement function that is suspending, and that is making all this body one after another. The question is, how does it work? How is it possible that we can do it this way? When you look at that, that you go and run on a UI thread, and then you release this UI thread, and you get back to that, and you continue, you might say that one does not simply stop function in the middle and continue it later. This is something that is obvious for the developers, but since Kotlin Coroutines, it is not anymore. I will show you how does it work under the hood on this simple example. This is getConfig function. It just do some printing, waits a second, prints something else, and then returns some string. This delay function is not the same as thread sleep. As you can see, it's not really blocking thread. Instead, it is suspending coroutine, and it is scheduling to continue this coroutine after some set amount of time. So this suspend coroutine returns so-called continuation. This is an interface of continuation, and continuation is built in the interface, and it has two functions: resume and resume with exception, and coroutine context that says how and where do we start this coroutine. So after set amount of time, we resume this continuation. What is this continuation? Where do we have it from? When we have suspending function, like this getConfig for instance, this suspending function is compiled into something like that. And as you can see, getConfig does not have any arguments, but under the hood it has argument continuation with continuation. Every suspending function has continuation passed as an argument. It's an extra argument that is generated under the hood. As a next step, it packs this continuation to make its own particular continuation. This coroutines example kt at getConfig is a special class generated for this single function. Every single suspending function has own class generated during compilation time. And then we have so-called state machine. So depending on what state we are, we'll have different code invoked. In the beginning, we have label set to 0, so we start from the beginning. We make top part of the code, print A. We set, before suspending point, we set continuation to next state, and then we invoke our function that is a suspending function, delay. And this suspending function, one more thing, this suspending function does not return string. It returns any. It is because it can either return string or it can return special pointer coroutine suspended. So it returns this pointer once it is suspended. So we call our delay, and delay the same, can either return unit or coroutine suspended. If it returns unit, it means it doesn't suspended coroutine. So in such a case, we would continue, get to second state, we have label equal to 1, so we print B and return from functions. This function wasn't suspended. If, on the other hand, and this is what actually would happen. Delay suspends coroutine, then delay returns coroutine suspended, and we return coroutine suspended as well. Notice that this is not a real implementation. The real implementation is far optimized under the hood. This is like how you can visualize actual implementation to make it, easy for you. So this is just a huge simplification. You can visualize it this way. So first we have our get config started with some continuation passed. If we launch it on launch Coroutine Builder, then this launch Coroutine Builder provides us this continuation. Our get config packs this continuation into Coroutine's example get config and starts delay with this continuation as an argument. This delay packs it into save continuation and invokes scheduler and asks scheduler to call it after a delay, to call resume after delay. Finish ends. Our delay returns coroutine suspended, so our get config returns coroutine suspended. It's ended. After 1 second, coroutine this continuation resume is called. So this is resume for save continuation. This particular class does nearly nothing. It only invokes the class, its delegate, so it invokes resume for Coroutine's example get config. I forgot KT. And this invokes our get config with this continuation. So this continuation is invoked but with next state, so it starts after the point where coroutine were suspended. And our get config returns string. I think it should be clear right now, at least clearer than it used to be. Let's look at a bit more difficult function. In here, we not only have two suspending points, but also we have state inside. So we have some nuices and some config. Again, it's optimized under the hood, but we can visualize it as something like that. As you can see, these variables are there, but there is an attempt to read them from the continuation. Since we use this special continuation class that was generated for this particular function, it has this kind of fields, so it can hold this configuration and these nuices. So we run with them. Let's suppose that nothing really suspends coroutine, so we start at coroutine at 0. Config and news are nothing important. We get config, so config is filled. Let's say it's a correct response, so not coroutine suspended. So we continue into state 1. The same, we update label, we get nuices. If it is not coroutine suspended, we can go next. We go into state 2. We use our variables and we show our nuices. Pretty simple. If, for instance, get config suspends, it returns coroutine suspended token, and we also return coroutine suspended. After some time, continuation will invoke our presenter on create, and all the data are on this presenter on this continuation, so they are filled, and we can continue from state where we finished. State after the state where we finished. So I think it's clear enough for you right now. What is important to understand is the distinction between Coroutine Support and Coroutine's library. Pretty everything I've showed you already was a part of Coroutine Support that is built into Kotlin. This support is built into Kotlin, but there is also Coroutine library that is distributed as a separate library. This Coroutine Support is pretty powerful. It gives us possibility to replace any concurrent style actually, while our library is giving us one concrete way how we can use coroutines. This Coroutine Support is pretty minimalistic. It uses only one modifier. It is suspended, and only few primitives like start coroutine or this suspend coroutine, and few interfaces like continuation or coroutine context. On the other hand, coroutine's library is much bigger, contains a lot of objects and functions. I still want to talk about coroutine support, and in detail, I think you might be interested that coroutines support can replace actually any concurrence style, or nearly any, that is in other languages. And Kotlin team was experimenting with that and made a lot of example how, for instance, Go concurrence system can be replaced on C#, etc., etc. So how does it work? Let's see some possibilities. And we will work on this, this simple example when we need to get some description, get some profile URL, and get some image using this URL. Obviously, these functions are needs a lot of time, so there should be invoked in some other context. I'm sorry. In callbacks, as we already told, we would do it like that. Direct equivalent in coroutines is following. It does exactly the same. It stops in every function. Once it's done, it goes into next function. The same as callbacks, but flat, cleaner, simpler. C# introduced async await native support. In Kotlin, we can, using coroutines, we can very simply make our own async await. This is practically everything to have async await once you have Kotlin coroutines. You don't need to read it. It's a lot of code. The point is that it's a very minimalistic. It's just, I don't know, 30 lines of code and that's it. And you can have async await. Just this await is a suspending function, so you need to invoke it on some coroutine builder or in async or in suspend function. So async await, very, very simple using Kotlin coroutines. No need to special support for these keywords. You can also extract this async await into separate functions. So this is a completable feature as an async await, and very simple as well. Sequence generators, another cool feature that can be found in languages like Python, but we hadn't got sequence generators in Kotlin. But since we have coroutines, it's actually pretty simple to implement it. It has nothing in common with concurrence, but we use here coroutines because I hope you understand the subject of sequence generators. We just want to generate a sequence like we do a function. So we start this function from the top, we get into yield, and this yield generates a value. Of course, it generates the value once we ask for this value because it's lazy. So in our komputer, jest ładowarka w tym. It starts from the top, gets into yield, and emits value. It emits as much value as we ask. So in this particular case, I asked for 10 values. So it will get into yield. It needs still 9 values. It goes in a while, gets into yield again, generates another value, etc., etc. After that, we can still later ask for next 10 values, so, and there is not a problem. Notice that coroutines are very, very light. We can use them and forget about them. We can copy coroutines. Copying coroutine, all the state of coroutine in suspension point is held in the continuation. So you can actually save this continuation somewhere. You can copy it if you copy fields, and you can use it on the same functions to start coroutine from suspension point. So this is lightweight and it's very, very simple. Another thing are channels. Channels known from Go and ReactiveX. Channels, there are a lot of examples how coroutines can be used to replace channels, but the very simple are following. There is a channel class in Coroutines. You can send events and receive these events. This is a bit more complex example when you set next letters from A to X, and after each send you wait 40 milliseconds, and after some time you can close it. Notice how for works. For waits for a next message on channel. So it's actually, since this is generating, channel is suspending iterable, and for is nothing else but iterating using iterator. So since it is suspending iterator, our for is suspending when it waits for next object. But when we close the channel, for loop is finished, and we can print finish. So this shows that coroutines, obviously we can do RxJava in Kotlin. It's a Java. I mean, you can use everything in Kotlin that can be used in Java. But thanks to Kotlin Coroutines, you can make RxJava and channels better and simpler. You can use for, you can use error handling, using suspending function. You can make possible a lot of things that were not possible before, and that make it just simpler. And this gives us a freedom. In general, the basic idea, and Kotlin team had it in mind, was to create support that allows us to reproduce any concurrence model, to not only give a freedom how we use concurrence in our language, but also to give a freedom to the developers to create library that implements new concurrence system. So if you have some concurrence system in mind, some newer, cooler, better than anyone possible, you don't need to implement it in the language. You can just make your own library and use Kotlin Coroutines to implement it, and chances are there won't be any problems, because if you can reproduce nearly any concurrence system there is, chances are that your idea for a concurrence system is easy to implement using Kotlin Coroutines as well. Okay, that's about built-in support. I wanted also to give you some tools to be able to start your adventure with Kotlin Coroutines. So I want to give you a basics of Kotlin X Coroutines. This is the Coroutines library, the most important Coroutines library right now. The first thing you need is a Croton Builders, because suspending context must start somewhere, and for that we have few Coroutine Builders. Let me show you that on the live coding. Okay, so the simplest Coroutine builder is launch. You can start, let's say, delay 1 second and print something. If you start it, it won't display anything, because your main would finish before this coroutine is finished. Coroutine is like a lightweight thread. It doesn't stop your program for finishing. So you need also thread sleep and some bigger value. Better implementation would be to replace this with run blocking. But first, what is run blocking? Run blocking is a very characteristic coroutine, because this is the coroutine that blocks main thread once it's suspended. It's the only coroutine builder I know. It's big enough. The only coroutine builder that does that. So if we make like delay 1000, print A, and then print B, we'll first wait 1 second, then we'll have A, then in 1 second, then we'll have B. So this delay blocks our main thread, so we can use it this way, and this will work the same as thread sleep, but we can also use job. Launch returns job. Job is a state of coroutine, and one of its function is join. Join is a wait for this coroutine to let it finish. So right now we'll have our I am done printed. Very common practice is to do it like that. And right now we can easily do job 1, job 2. And yep, start it. Bum and bum. Yeah, the second one prints pretty immediately because it's already after delay, so it just needs to get a thread and work. Sorry, first one print 2 is invoked because it waits only 1 second, so we need to wait for job 1 a bit longer. Another very important is async await. Async returns some value. And works pretty the same as we've seen it, the same as in C#, print v1, oops. But here we will have I am done printed always first because it's printed in here, and then I wait for v2. It's already calculated, so it will be printed immediately after. These are my examples for all of this with some measurement, and you can see that the same as what I've already showed you. Another important thing is coroutine context. Common pool is a default coroutine context. Coroutine context is a bigger subject, but one of the characteristics of coroutine context is that it says on what thread we execute our coroutine, and this is the most important characteristic actually. So common pool uses common pool of threads to start this coroutine, and it is default coroutine context, so you don't need to specify it. UI thread is asking to run your coroutine on the main thread, but what is a main thread in a Kotlin Coroutines library? There is not such thing. You need additional library to provide UI for Android, for JavaFX, and for Swing. Another, you can use coroutine context because when inside coroutine context, I can show you actually. Inside coroutine context, you have, let's say, launch. You have some extra functions that can tell you about your actual coroutine. So you can obtain current coroutine context. You can check if it is active. And I think that's pretty it. Yep, coroutine scope for launch does only that. And you can use coroutine context. Actually, you should use coroutine context if you want to cancel sub-coroutines that are created inside coroutine when you cancel your upper coroutine. And the last one is uncoffined. Uncoffined, it doesn't change context at all, so it uses previous context. It's the laziest one. Coroutines are supported by Retrofit. I think also by other libraries, but Retrofit is very popular one. thanks to some additional library. One of them is Coroutines adapter made by Jake Wharton. It works like that. We just add additional adapter factory, and then you can use deferred interface as a return type for your service. And deferred has a wait function which is suspending, so you can actually use your API as a suspending function without any additional wrapping. This is how you cancel job. You just use job and job cancel. It's actually very important if you are, for instance, an Android developer, because you cannot finish your activity without canceling your jobs inside. Otherwise, you would have data leaks. So it's pretty helpful. In using coroutines, you can make great backend, and there are already backend frameworks that support that. One of them is Cater, I use on my projects, and it uses coroutines out of the box. These get propositions and get accepted news data are all suspending functions because this get is actually a coroutine builder. Get, put, etc. Also, you can unit test coroutines, no problems with that. There are libraries like mock, very good mocking library similar to Mockito but designed for Kotlin, and it also supports to use coroutines in every and verify block. You just need to use co-every and co-verify, so you can record the sequences, you can say what result do you want to have, and do pretty everything that you can do in normal mocking in Kotlin. Oh, I haven't added the link, but it's a mock library by using 2K. Very nice mocking library for Kotlin. If you want to see whole multi-platform system that uses coroutines, check out my application Kotlin Academy app. I have Frontend. It's a Kotlin JS. It's actually JavaScript frontend written in React, written in pure Kotlin. It has Android application, also written in Kotlin. It has watch application, written in Kotlin, and it has backend. And everything uses coroutines, including common modules, because this multi-platform project in Kotlin can have common modules. And so we can reuse code, and coroutines are supported in common modules. So I have a part called Common Client that has all the presenters, and it uses intensively coroutines, and of course it's unit tested, and it's in common module. It's both compiled into JVM bytecode and into JavaScript code. Soon it's going to be also compiled into native code for iOS. And that's it from my side. I hope that you liked. You are a great audience. I see concentration in your faces. So thank you very much for your attention.